So the topic now is relativistic formulas. Here's the non-compounding first principles formula. And down here are the Doppler formulas, non-relativistic and relativistic for wavelength and for the ratio of the final observed wavelength over the initial wavelength. So we can see that this middle term here in the non-relativistic first principles formula has the form of this term in the Doppler non-relativistic formula, which makes sense because when we built that, that was the Doppler redshift component. So all we have to do is replace this by the relativistic formula, which looks like that. So this is the relativistic first principles non-compounding formula. And at the present time, I won't do anything more with that, but I will discuss for a couple of minutes when it would be appropriate to use that and when it's a sufficient approximation to use the non-relativistic formula. And here's a quick look at the difference. If we use a first principles H value of 36 and an object with dL of 100 megaparsecs, then the non-relativistic formula V over C, 36 times 100 over 300,000 is 0.012. If we use a relativistic formula, 1.012 over 0.98 minus 1 equals 0.01207. So the difference, that's the difference between using the two formulas. And the percentage difference is that bit. 0.7 over 120 is 0.61 of 1%. So the relativistic formula would be more accurate by this much, or more correctly stated, the non-relativistic formula will understate the redshift by that amount. Now remember that this quick estimate is for dL, but the relativistic issue arises for d1. We know that d1 is less than dL in all cases observed to date, which means that the percentage difference for d1 would be less than this at a distance of dL is 100 megaparsecs. The same kind of quick analysis for dL equals 500 megaparsecs. The difference is 3.16%. Another way of looking at where the breakpoint might be, where you might want to use the relativistic formula, is that it's sometimes said that relativistic formulas should be used whenever velocities go over 1% of the speed of light. So that 1% of the speed of light is 3,000 kilometers a second. We're talking about d1, so the formula is v1 equals h1 times d1, so 3,000 divided by h would give us the distance in megaparsecs that would be our breakpoint. If we took h as 36, 3,000 over 36 is 83.3 megaparsecs. So once someone has given us a simple to use relativistic formula, that might be a point for stars, supernovas, galaxies, and so on that are being used at distances where DL is greater than 83, then we know that D1 would be in the safe range to use the relativistic formulas. But really, as we've seen, for most purposes, even up to distances of 500 megaparsecs, the change in the calculation is not that great. It's not doubling or of an order of magnitude. It's down in the range of 1 to 3% of that middle term, so not of the final answer of H, but of the middle term for ranges or distances up to DL equals 500 megaparsecs.